This is the 5th lecture for Text Unit 6 about atoms and their electrons. This lecture continues our discussions of electron configurations and orbital diagrams for atoms. Before we go further, I want to define a couple of terms, core and valence, to describe electrons. In an atom, the valence electrons are the ones with the highest N. So if you can determine the N values of the electrons, you know which ones are valence. These are also the ones that are farthest from the nucleus. The core electrons are all the others. In other words, if it isn't valence, it has to be core. Many, often all, of the core electrons in an orbital diagram or electron configuration can be symbolized with a noble gas core abbreviation. So what is a noble gas core abbreviation? In an orbital diagram, this abbreviation replaces core electrons. It can replace all the core electrons from the previous row of the periodic table in a noble gas configuration. Let me illustrate with the carbon atom. Here is an orbital diagram for the carbon atom. 1s, 2s, 2 electrons and 2 p orbitals, as we saw in the last lecture. Here, 2 electrons in a 1s orbital. First, you'll notice these are core electrons, and the valence electrons are these 2s and 2p electrons with n equals 2. These n equals 1 electrons are core. Also note that this looks like an orbital diagram from the noble gas at the end of the previous row. Noble gas core abbreviations have to be noble gases. This is essentially the electron configuration of helium. So you can replace it with a symbol for helium in brackets. And this abbreviates the orbital diagram. Alright, now you have looked at orbital diagrams for the third row element without the core abbreviation. Try writing orbital diagrams for the third row elements using the core abbreviation before checking your answers on the next slide of this presentation. Here are the orbital diagrams. First, note they look like the orbital diagrams from the last lecture, except that the 1s, 2s, and 2p electrons have been replaced with a symbol for neon. That portion of the orbital diagram is identical to the orbital diagram for neon and replaces those electrons in the diagram. The valence electrons are the n equals 3 electrons, and those still appear, and we see the 3s and 3p subshells getting filled with electrons as we go across the row. Note that when we reach the end of the row, argon, the 3s and 3p subshells are filled. This, by the way, is a correct orbital diagram for argon. You can't replace the entire diagram with a symbol for argon in braces. Alright, and it's now time to move on to the fourth row. N equals 4 for the valence electrons. We notice that we're in the fourth row. We start putting the valence electrons have n equals 4. First 2 electrons go into an s subshell, the 4s subshell. And you've probably recognized by now that every time we are looking at elements in the first 2 columns of the periodic table, we're putting electrons in an s subshell. So here are the diagrams for potassium and calcium with core abbreviation, in this case the argon core abbreviation. Notice that the core abbreviation saves a lot of work in writing and displaying the orbital diagram. The 3D subshell is next to be filled looking at the energy diagram for subshells from the last configuration. Note also that we move now into the transition metal block of the periodic table. Generally, when looking at elements in the transition metal block, we will be putting electrons into d subshells. So here's the orbital diagram for scandium, 2 4s electron, 1d electron in the 3d subshell. Note there are 5 orbitals in the 3d subshell. Note it's easy to count d electrons in the periodic table. Scandium has 1, its next door neighbor titanium has 2, vanadium has 3, for example. Here's an orbital diagram for the vanadium atom, 2 more d electrons. Note we obey Hund's rule, putting electrons into a d subshell. Now looking at the periodic table, we would predict 4 3d electrons for chromium, but it has 5 and only 1 4s electron. In other words, here is the predicted orbital diagram for chromium you would obtain using the rules we have learned up to this point. However, the correct orbital diagram is an exception. An electron has been taken from here and put into the d subshell. Here is the correct orbital diagram for chromium. This is an exception to the rules, and you must memorize this exception. So again, chromium atoms are an exception to the rules for making orbital diagrams. Alright, let's jump a ways across the periodic table. Nickel is unexceptional, so you should be able to draw an orbital diagram for the nickel atom before moving on. Nickel has 8 d electrons. You can verify that by counting on the periodic table. So here is an orbital diagram for the nickel atom. We put 5 d electrons in the 3d subshell first, and then we have to pair the next 3 electrons we put in. We fill from the left to the right by convention. So this diagram is straightforward and predictable. However, when we come to the next element, we predict 9 d electrons for copper, but they are actually 10 and 1 4s electron. So here is the predicted configuration for copper. Here is the correct configuration for copper. You must also note this exception. So 2 exceptions in this row. Chromium and copper have an electron move from the 4s into the 3d subshell. In the case of chromium, the reason generally given is that this creates a half-filled 3d subshell, which is stabilizing. And in the case of copper, this creates a filled 3d subshell, which it is argued, and it's argued that filling a subshell of electrons is stabilizing. Alright, these are 2 famous exceptions that you must know for this course. You should be able to write a diagram for zinc because zinc is unexceptional. Has 10 3d electrons, so we have the argon core, 2 4s electrons, and 10 3d electrons. Add 1 more electron and you can have an orbital diagram for gallium. Next electron, according to the energy chart, goes into the 4p subshell. And notice at this point we've moved out of the transition metal block. Periodic table can be used to count p electrons, starting from column 3a. Gallium has 1 4p electrons. Try writing diagrams for arsenic and krypton before moving on in the presentation. Alright, arsenic has 3p electrons, so its orbital diagram looks like this. Note the similarity to the orbital diagram for nitrogen. Same arrangement of s and p subshell electrons. Likewise, krypton has 6p electrons from counting, so this completes the 4s and 4p subshells, and at the same time completes row 4 of the periodic table. Alright, what I have done next is selected 4 elements from row 5 for which you could attempt orbital diagrams before we continue. In row 5, naturally, the core abbreviation is for krypton, and strontium has 2 5s electrons. You could have predicted that from its position on the periodic table. Rhodium has 2 5s and 7d electrons from counting on the periodic table. So here is rhodium with the 5s subshell filled. And 7 electrons in the 4d subshell. Tin has the 5s and 4d subshells filled, and we predict 2 5p electrons. Iodine, we predict a total of 5p electrons, so we have more electrons in the p subshell of the orbital diagram. Notice the similarity of tin to carbon and of iodine to the other halogens in terms of its arrangement of s and p electrons. Alright, moving into row 6. Barium is predictable. Its electron configuration is xenon core 6s2. So here's an electron configuration. And here is the orbital diagram for barium. The next element we come to, lanthanum, is an exception. From our charts, we predict that lanthanum should have a xenon core, then 6s2, and 1 electron in a 4f orbital. The correct orbital diagram has 1 electron in a 5d orbital. This is another exception to know. Okay, so here is the predicted configuration, diagram for lanthanum. Notice that there are 1, 2, 3, 4, 5, 6, 7 orbitals in an F subshell. L equals 3. There are 7 values of M sub L. But the correct diagram doesn't have that electron in 4f, but instead in the 5d subshell. Now, if you look carefully on your periodic table, counting atomic numbers, you'll notice that the elements following lanthanum, the lanthanides, are at the bottom of the periodic table. This block of the periodic table corresponds to filling a 4f subshell, which is the next one in energy. You can count 4f electrons. Now, you have to be a bit careful when you do this. You have to start counting back at lanthanum, then jump down to the lanthanides. So in the case of promethium, there are 5 4f electrons. In the case of ytterbium, if you count, there are 14 4f electrons. And that completes or fills the 4f subshell. Yet there's one more element down here among the lanthanides. The last lanthanide electron for lutetium, goes into a 5d orbital. Then we jump back to row 6 in the d block right beyond lanthanum, and we can predict d electrons again. For example, it's very easy to count that tantalum has 3 5d electrons. 6s and 4f subshells are filled. Here is a diagram for Mercury, which has 10 5d electrons. Alright. At this point, you should be able to try polonium and astatine before moving on. We're in the P block of the 6th row at this point. We can readily count 4 p electrons for polonium. Those means 4 electrons in the 6p subshell. Note the arrangement of s and p electrons is similar to oxygen and sulfur. Astatine has 7 6p electrons, so here's its orbital diagram with 5 electrons in the 6p subshell, not 7. You can count 5 6p electrons for astatine. Alright, let's look at row 7. Francium and radium begin the S block. Actinium is an exception. The electron configuration is radon core 7s2 6d1 instead of radon core 7s2 5f1, which you would predict from our energy chart. In other words, here is the incorrect diagram that we would predict, and here is the exceptional correct diagram. Alright, this is the last of 4 exceptions you must know for this course. And notice it's very similar to lanthanum. An F electron is replaced with a D electron. Similarly, beyond actinium are the actinides. And as we put electrons into the actinides, we will be putting electrons into a 5f subshell. So for example, here is a plutonium diagram. We predict 6 5f. Note that counting electrons is a little tricky in the actinides, just as in the lanthanides. We start counting at actinium, so there are 6 5f electrons for plutonium predicted. Lawrencium, at the end of the row, will have its 5f subshell filled and 1 electron in a 6d orbital. Alright, at this point we could object to high atomic number synthetic elements from nuclear labs like seaborgium, which has, we predict by counting 4 6d electrons, and I include an orbital diagram for that element here. At this point, you should be able to draw an orbital diagram for any element on the periodic table, including 4 exceptions. I will tell you there are other exceptions on the table we have not discussed in this course. Alright, this concludes this presentation for Unit 6.